Hello and welcome to Micromaterialism. This is the series where we take an exciting topic of material science and we break it down to a bite-sized episode that's about 10 minutes. And as always, we're appreciative of our supporters. Today we're sponsored by Materials Today, that's an Elsevier publication, and mapmatch.com, so check them out. Andrew, what are we talking about today?
So a little while back, we were riding in a car, and we were discussing some technological failures that involve material science. We thought this was a great way to contextualize the importance of a lot of concepts that often just get glossed over when you're taking the class or when you're thinking about materials. So we thought it'd be great to touch on one of those. And Sparks recently turned us on to this great Twitter thread from @TubeTimeUS. We'll link to his account in the description so you can check it out. Talking about this fascinating story of a transmission tower that was responsible for the 2018 fires in California.
Yeah, think back to this. You probably saw the pictures. It was absolutely incredible. The town of Paradise, California was just reduced to an absolute charred rubble. It was unreal. In fact, this wildfire, it was the Camp Fire is what it was called. It was the most expensive natural disaster in the world in 2018 in terms of insured losses. It was something like $16.5 billion of damages. And besides just the monetary loss, there was 85 people that died in this fire and something like over 18,000 structures that were burned. So this was horrific. Now, what we found interesting about that is that when it comes to wildfires, it's usually, neglect, negligence, or lightning or something like that. You don't typically think to yourself like, oh, that's probably a materials failure that caused that. And yet he does this fascinating job of pointing out that there was material failure involved in this. Talk us through it, Andrew.
Okay, before we get into what materials were involved, though, I think we need to talk about the structure of a transmission tower for those unfamiliar. So transmission towers are generally carrying very large current wires, trying to get current and electricity over long distances. So you have the metal tower, the structure, right? Suspended from that are the wires carrying the electricity. However, you don't want that much current touching metal. So they're usually suspended and connected via insulating materials as well. So these materials prevent the transfer of current by not having any loosely bound or free electrons. In material science, you can think of this as the material having a very large band gap. And this contributes to it having a very high dielectric resistance to the transfer of charge.
And what's crazy, if you look at power and efficiency of transmitting power long distances, you could either go with high current, but if you go to high voltage, you can minimize the current. And so they go to crazy high voltages. Those big power lines you see, they can carry hundreds of thousands, typically on the order of about 100,000 volts. And so if you have that enormous difference in potential, you could have this arc, right, and spark very easily. And that's why they have to have these dielectric materials preventing them from touching the tower, grounding out, and then you causing a fire. So how did the fire start? What happened?
Right, so the way that they attach the insulator and the cable to the metal frame is it's attached via something they call a C-hook. You can tell it's a C-hook by the way it is. And this C-hook sort of just fits into a loop that's hanging from the tower, and that's where it sits. And
so to paint a picture like this, the little plates, as you will, like this, the porcelain discs are attached to the C-hook, like they're vertically stacking it down. Mm-hmm. That's connected to the tower, and then that would be connected to the wire.
Yes.
Okay, gotcha.
Right, and because the hook's clipped in through a hole, it allows it to rotate a little bit. So
yeah, because there's wind and stuff, that makes sense.
Right. So what ended up happening was over time, this C-hook started to wear down, right? It started rocking back and forth, and it wore through the metal that it was locked into. And eventually it wore so much that it just fell, causing the wire to now no longer be suspended and come into contact with the rest of the tower.
And as soon as you have 115,000 volts touching metal,
it just liquefies it.
Yeah, the current's like, why am I going to bother going through this high resistivity, pathway when I can take the path straight to the ground? So you dump an enormous current. These power lines carry 500 to 1,000 amps typically. And that all went immediately into the aluminum of the structure, which gets liquefied. Now you're spraying molten aluminum all over the hot, dry ground, and next thing you know, you've got a fire. All right, so wind is not exactly an unexpected thing. Like, clearly they knew that it was going to be windy, and so they would not need to inspect for this. What does that process typically look like?
Right, so they're aware that these things eventually wear out. But a lot of these transmission lines, right, they're not in your main public areas. They're often in somewhat remote areas that are hard to get access to. So they usually just fly a helicopter and kind of inspect it that way, which can cause some problems when you're trying to look at small details, but from a helicopter
Metallurgy
makes it a little bit difficult.
from the air. All right.
Yeah, it's like even more than macro analysis. But in this case, normally they also keep records, right? They probably have some expectation of when components are going to fail, and then they say, okay, we should probably go inspect this at this time, and maybe do a more detailed inspection as well.
And I know that on the power line that did fail, that there was evidence that the initial bracket had been bypassed because it had worn so much, and they had actually installed a new L bracket and put the C hook into that. So they must have known at least at some point that wear was happening, and they were trying to make sure that it didn't get out of hand.
Right. The problem in this case was that it wasn't so much that they didn't know, as in they lost records. The company that was responsible for maintaining and operating these transmission lines had lost pretty much all of the records of maintenance up to the year 2000. So they had those 18 years, but they estimated that this line had been in service since 1921, so 97 years old at the time of this fire.
Which, it's not uncommon for these C hooks. I was reading that they can have lifetimes of about 100 years. That's not like it's uncommon, but you would never just let it run until failure. I read one of the examples I saw on this. It'd be like buying an old car, like a used car, never putting oil in it and just running it until it was completely toast. That's essentially what happened here.
Yeah. It was definitely some negligence, and it really highlights the importance of what we want to talk about in this episode being understanding failure and when materials fail, but also documenting and keeping records and making sure that they are records that are going to last. So the FBI got involved because it caused so much damage and was saying, okay, what happened here? What was the cause? So I didn't know this, but the FBI has a metallurgical unit in Quantico, and they determined that the C-hook...
Somewhere out there, there's a listener who's like, oh my gosh, my dream job. I didn't know it existed, and there it is.
Apply. But they took it to their metallurgical lab, and they did analysis, and so they determined that the C-hook was made of cast iron. Now...
Super brittle, super hard, right? High content. The more carbon you put in things, the more it behaves like a ceramic, right? You're getting more and more of that cementite phase. Now, what's the bracket made out of?
I think a lot of these towers are made of aluminum, or it might be some other steel, but definitely a softer material if it's able to wear through it. This brings us to the concept of hardness, right? Hardness is a measure of resistance to localized plastic deformation. So this can be induced by mechanical indentation or abrasion over time. And, the simplest example, I think, in elementary or middle school, they always go over like, oh, if something is harder, it can scratch a softer material, right? Like a pencil can't scratch diamond, but diamond can scratch a pencil, even though they are made of the exact same element. But, something that's harder is going to be able to wear and degrade something that's softer if they're against each other. The main point to get across is that if something has stronger interatomic bonds, then it's going to be harder, right? If it has a structure that makes it stronger as well, it's going to be harder. And so harder materials are going to scratch softer materials.
Yeah, if there's any rock climbers out there, this is like one of the important things they teach you when you're setting up anchors, is that if you have, for example, your webbing and then you have steel carabiners, you would never put aluminum onto that steel carabiner because it can actually damage it or, heaven forbid, wear through it. So that seems to be a very real possibility of what happened here. But again, there's not good record keeping. And actually, there was a lawsuit involved in this. And I think the power company actually ended up admitting guilt to involuntary manslaughter in the end.
I didn't follow through with the case, but if they pled guilty,
yeah,
I'm sure it probably went through that way.
So we're going to do lots of future episodes on this idea of materials failure. But here's just a few things to think about that you probably learned as a material science student. Why do we study failure so much, and what are the aspects of it? One thing that we always teach in material science is probabilistic failure analysis. If you ever took a course where they talked about Weibull analysis, I might be causing PTSD by bringing it up, but it's worth learning about it. And here's the reason why. Think about this. Think about failure under two scenarios. One question might look like this. What is the yield strength of this alloy? Now consider this question. What is the probability of yielding for this alloy under these conditions? Well, which one's more useful? Obviously, the second one, right? It's not enough just to look up on a material spec sheet and say, oh, this has a yield strength of 500 megapascals, great. Because use conditions could really matter. Like, are we asking about after 20 years of service, right? Or are we talking about when will one component fail out of a million? So probabilistic failure analysis becomes a really important part of material science. What else do we talk about when we talk about failure, Andrew?
A lot of not a buzzword, but a big word that often comes up is the idea of a safety factor. And so we have some sort of scaling factor that we want to apply to whatever our expected stress is to sort of over-engineer our material in order to meet that. So we have an expected stress it's going to go under, and we want to make sure that it is some safety factor above that expected stress. And it's typically like a multiplier, some sort of scaling factor.
Yeah, and a lot of engineers think that is like the way to think about failure. And what I strongly encourage them is to move away from the very simple safety factor approach to the more nuanced probabilistic failure analysis. Because really, it's not just like, oh, I'll just apply a safety factor of 3, because you don't know if that's good enough. It's good enough if you know that only 1 in 300 components can fail, and then you can probabilistically design for it. Another thing that we learn about material science are these complicated things like stress rupture, right? Which are these long life testing. Let's say that something needs to survive in a furnace at some high temperature for 10 years. You don't have 10 years to test it before you want to sell your product, maybe. So how do you know if it's going to survive? Well, what you can do is you can put it at an even higher temperature. So this idea or this concept of accelerated testing is actually done all the time in materials development. They'll put things under high humidity, high temperature, high strain rate to sort of make it a more severe scenario. And you can actually model this if you understand the relationship between the increasing severity, like temperature or strain rate, and how that scales with temperature or with rate or whatever. Other things we cover are things like steady state creep strain rate or slow crack growth. Any introductory material science class went over these things. And the whole point to them is that you can use them to model and approximate different regions. So you can get an idea for how long something will fail if you know the rate at which it's declining in performance, whether that's strain or crack growth, whatever it may be.
If you're in an introductory material science class or strength of materials, a lot of times when they're talking about cracks or deficiencies, they're really only covering the first or second phase of that, right? Where it's linear and easy to predict. But once you get to the tertiary phases, where things start to ramp up and you see even more propagation, that's where it's a little more difficult to model and a little more difficult to predict too. And so we've been getting a lot better at modeling those, a lot of times through machine learning and looking at past failures to try to predict future ones. But that's something that it can be hard to think about with just regular equations. We really do have to dive deeper for those.
Okay, as always, you can find links to all the content that we covered in this in our show notes. And you can hit us up with questions, episode suggestions, internship offers for these wonderful people I'm working with by checking out any of our social media accounts. We probably check Instagram the most. That's at materialism.podcast. A huge thanks to Call White for the music for our intro and outro, and we'll see you guys next time.